Okay, that last video ended a little bit abruptly. My memory card was full and I wasn't aware of that. I actually thought the video ended a little bit later than it did because I sort of kept talking and writing on the board and then my camera made a noise. And so I thought I had gotten through the entire phase portrait. So I went ahead and made the next video. So when you're watching this, in this video I'm saying, oh, the last video ended rather abruptly. The next video will start exactly the same way because I thought that I had gotten through this, and so I went ahead and made the video that actually comes after this. Now I'm coming back to say, oh, I really would like to finish this phase portrait. Okay, so we were trying to get the orientation of our curves. So we had gotten the orientation of the curves along the x-axis. Let's do the same along the y-axis. Okay, so remember along the y-axis, of course, x is 0, and that makes xy also equal to 0, which makes cosine of xy equal to 1. So up here on the positive part of the y-axis, y is positive. Now x prime is going to be 0 because x is 0. Y prime, we've got the opposite of a positive number times 1, so y prime is going to be negative, so we're coming down along here. On the negative part of the y-axis, we'll have the opposite, because now I'm plugging in a negative number for y, and that's going to make y prime positive. So on the negative part of the y-axis, we're moving up. Okay. Now, this was an equilibrium solution. Every point on the pink and green curves is an equilibrium solution. This green curve corresponded to where x times y was pi over 2. This pink curve is where x times y is 3 pi over 2. Those are going to make cosine of xy 0. So this pink curve here isn't actually a solution curve. It's infinitely many individual points, each of which is an equilibrium solution. Okay. So I want to look at the orientation of my other curves. So let's take a look at this blue curve. That corresponded to x times y equaling pi. Notice if x times y is equal to pi, cosine of xy is negative 1. Now, this curve is in quadrant 1, so x and y are both positive. So here I will get a positive number times negative 1. That's going to give me a negative. Here I get the opposite of a positive, so a negative times negative 1. That's going to give me something positive. So that tells me x prime is negative, we're going to the left. Y prime is positive, we're going up. This curve is oriented this way. Now if I go to the next blue curve, that was where x times y was equal to 2 pi. Now that's going to make cosine of xy positive 1. This is still in quadrant 1. So x and y are still positive. So this is going to be a positive times 1. This is going to be a negative times 1. This time x prime is positive and y prime is negative. So this curve is going to be oriented this way. So it's kind of interesting. This pattern will continue. Between the curves that are equilibrium points, the orientation will be consistent because I'm not going to be able to have that change here in the middle. But every time I jump over one of these lines of curves of equilibrium solutions, the orientation of my curves changes. Okay. Notice here in between these curves, which corresponded to where xy was 0, and this curve, which corresponded to where xy was pi over 2, I would have solution curves that were coming this way. That's going to be consistent with down and to the right. Okay. Over here, we would go down and to the right here to be consistent with these boundary curves that are the x and y axis. When we cross the pink line, that's going to reverse. When we cross the green line, that's going to reverse. Here, we're going to be going up and left, then down and right, then up and left, and it's always going to alternate. And you can pick, if you want to pick a particular curve, find what xy is on that curve so you know whether cosine is going to be positive or negative. And then look at what quadrant you're in to see whether x and y are positive or negative. And you can confirm that this pattern continues throughout. Kind of neat. So if we look at our equilibrium solutions, it looks pretty clear from this picture that this equilibrium solution is going to be a saddle. I could certainly linearize the system and confirm that, but just from the phase portrait I can pretty much see that this is a saddle. The other equilibrium solutions I'm not going to be able to classify because they're not isolated points. They're part of a curve, which is a whole bunch, infinitely many equilibrium solutions all right next to each other.